Okay, here is an audio narration based on the provided information suitable for TTS. Let's discuss transformer placement within a hospital's emergency power system, specifically concerning a 480-volt generator supplying 120 208-volt critical branch circuits. We have two primary options to consider. Option 1 involves placing a single transformer on the load side of the transfer switch. This setup offers a few advantages. First, it simplifies the wiring and reduces the overall number of devices in the system, potentially lowering initial installation costs. Second, and perhaps more importantly, the transformer is continuously in use. This constant operation minimizes the risk of failure due to inactivity, which can be a concern for transformers that sit idle for extended periods. However, this configuration presents a significant drawback. If this single transformer fails, it will interrupt both the normal power and the emergency power supply to the critical branch. This is obviously undesirable in a hospital setting where a reliable power source is paramount. Option 2 involves utilizing two transformers, placing one on the line side of the transfer switch for the normal power source and another on the line side for the emergency generator source. This approach offers the critical advantage of redundancy. If one transformer fails, the other can maintain power to the critical branch, ensuring uninterrupted operation. Furthermore, this arrangement allows for maintenance or replacement of one transformer without completely shutting down power to the critical systems. Despite these benefits, this option also has its downsides. The wiring becomes more complex, and the system includes more components, potentially increasing the initial cost and complexity of maintenance. Crucially, one transformer will likely remain unused for prolonged periods, potentially increasing the risk of failure where it is suddenly called upon to operate. Considering the critical nature of a hospital's emergency power system, the preferred solution is option 2, employing two transformers on the line side of the transfer switch. While this arrangement is more complex, the redundancy provided significantly outweighs the disadvantages, ensuring the highest level of power reliability for critical systems. Beyond the basic configuration, several additional factors deserve careful consideration. First, load balancing. If the load on the critical branch is substantial, selecting transformers with a higher capacity becomes essential. This ensures proper load distribution and prevents overloading, which could lead to premature failure. Second, maintenance. Establish a regular maintenance schedule for both transformers. They should include visual inspections, testing insulation resistance, checking for overheating, and verifying proper operation under load. Regular maintenance is crucial for identifying and addressing potential problems before they escalate into failures. Third, monitoring. Implement a monitoring system to track the status of the transformers. This system should monitor key parameters such as voltage, current, temperature, and oil level, if applicable. The system should also be configured to alert personnel immediately in case of any anomalies or deviations from normal operating conditions, such as over temperature or under voltage. This early warning system enables proactive intervention, preventing potential failures and minimizing downtime.